Here's a question that will genuinely bother you once you think about it. What if one of the most geologically active, chemically complex, and scientifically revolutionary objects in our entire solar system was sitting right in front of us for 76 years, and we completely ignored it because we were too busy arguing about what to call it? That's not a hypothetical. That's exactly what happened with Pluto. We put it in textbooks, we hung it on classroom walls, we gave it the last spot on every solar system poster ever printed, right after Neptune, that tiny blue dot at the edge of everything. Then in 2006, the International Astronomical Union held a vote, reclassified it as a dwarf planet, and the world collectively shrugged and moved on. Pluto became a punchline, a pop culture reference, the planet that got fired. And here's the thing, while we were busy mourning its demotion, writing the jokes, printing the revised textbooks, and arguing in comment sections, Pluto was out there, 5.9 billion kilometers from the sun, doing something that should have been impossible. It was alive. Not alive in the biological sense, though we'll get to why even that isn't completely off the table. Alive in the geological sense, active, dynamic, churning, running glacial systems, building mountain ranges, potentially erupting ice volcanoes, brewing complex organic chemistry in its atmosphere, and possibly harboring a liquid water ocean that has existed since before anything was alive on Earth. Every model we had said none of this should be happening. The math said it couldn't. The physics said it shouldn't. The scientific consensus going into 2015 was unanimous. Pluto was a dead, frozen relic, a leftover chunk of debris sitting in the dark, doing absolutely nothing. The scientific consensus was catastrophically wrong. When NASA's New Horizons spacecraft made its historic flyby on July 14, 2015, after 9.5 years of travel and a journey spanning nearly 6 billion kilometers, what it found didn't just surprise scientists. It didn't just challenge assumptions. It broke the models. It forced a fundamental rethinking of what small, cold, distant worlds are capable of. And it raised questions about the outer solar system that we are nowhere close to answering. This is the story of what we actually found on Pluto. And I promise you, nothing about it is what you expect. Before we get to the discoveries, you need to understand just how wrong the predictions were. Not slightly off, not in the right ballpark, but missing some details. Fundamentally, completely, spectacularly wrong. Start with the basics. Pluto orbits the Sun at an average distance of about 5.9 billion kilometers. To put that in perspective, Earth is 150 million kilometers from the Sun. Pluto is roughly 39 times further out. The sunlight that reaches Pluto's surface is about 900 times dimmer than what you feel on a summer afternoon. Noon on Pluto looks like deep twilight here. Not dusk, not early evening. Deep twilight, the kind where you're squinting to make out shapes. The surface temperature sits around minus 230 degrees Celsius. That's not just cold in the way that Antarctica is cold, or even the way that space is cold. That's a temperature at which nitrogen, the gas that makes up most of our atmosphere, doesn't just freeze into a liquid. It freezes into a solid. The air itself becomes rock. You can walk on frozen air on Pluto, if you can call what's on Pluto's surface walking. And then there's the size. Pluto is roughly 2,377 kilometers across, smaller than Earth's moon, smaller than 7 other moons in our solar system. Small enough that when the debate over its planetary status erupted in 2006, one of the main arguments against it was simply that it was too tiny to matter. Put all of that together, tiny size, almost no sunlight, temperatures that freeze the atmosphere solid, and the scientific conclusion was straightforward. Pluto had to be geologically dead. Any internal heat it ever had from its formation would have radiated away billions of years ago. There was no external energy source to power geological activity. There was nothing pushing anything, heating anything, or moving anything. Pluto was supposed to be the most inert, most static, most featureless object we'd ever bothered to photograph up close. That was the model. That was the consensus. That was what every planetary scientist expected to see when New Horizons arrived. What they actually saw made some of them question whether the spacecraft had malfunctioned. New Horizons launched in January 2006, the same year, remarkably, that Pluto was demoted. It traveled for 9.5 years, covering nearly 6 billion kilometers, before making its closest approach on July 14, 2015. It passed within 12,500 kilometers of Pluto's surface at a speed of about 49,600 kilometers per hour. Here's what makes that encounter even more remarkable. The spacecraft couldn't slow down. It couldn't orbit. It couldn't go back. It had exactly one shot, a window of hours, to collect as much data as possible before hurtling onward into deep space. Everything you're about to read came from that single frantic pass. After the flyby, it took 15 months for New Horizons to transmit all of its data back to Earth. The signal, traveling at the speed of light, still took over 4 hours each way. Scientists received the information piece by piece, and piece by piece, the old version of Pluto was demolished. The first image that stopped everyone cold showed a region that would later be formally named Sputnik Planitia. It's an enormous expanse of nitrogen ice sitting inside what appears to be an ancient impact basin, roughly 1,200 kilometers across. From a distance, it looked smooth, almost unnervingly smooth. That smoothness was the first alarm bell. In our solar system, virtually every old surface is covered in impact craters. Craters are how planetary scientists read time. The more craters, the older the surface. The Moon is covered in them. Mercury is covered in them. Mars has regions pocked with billions of years of impact history. Sputnik Planitia had almost none. The surface appeared to be less than 10 million years old. On geological timescales, 10 million years is nothing. The dinosaurs went extinct 66 million years ago. In cosmic terms, Sputnik Planitia's surface was resurfaced practically yesterday. Something had been actively erasing craters. On a world with no energy source, in temperatures that freeze nitrogen solid. That was only the beginning. When the high-resolution images from New Horizons came back, the apparent smoothness of Sputnik Planitia revealed something extraordinary. The surface wasn't flat at all. It was divided into irregular polygonal cells, each one roughly 10 to 40 kilometers wide, separated by shallow troughs. Scientists described them as looking like the cracks on the top of a cooling pot of oatmeal. That comparison turned out to be more accurate than anyone intended. Those cells are convection patterns. The nitrogen ice in Sputnik Planitia isn't static, it's churning. Warmer ice from below rises slowly to the center of each cell, spreads outward, cools, and sinks back down along the edges, completing one full cycle roughly every 500,000 years. The entire plane is turning itself over like a slow-motion lava lamp. On a world that was supposed to be frozen absolutely solid, the ice is moving, which immediately raises the most important question in all of Pluto science: where is the heat coming from? Pluto has no tidal heating. The moons of Jupiter and Saturn, Europa, and Enceladus, Io, generate internal heat because they're constantly being gravitationally squeezed and flexed by their massive parent planets, like a stress ball being worked over by a giant hand. That mechanical energy converts to heat, keeping their interiors warm. Pluto has no such relationship. It orbits the sun, not a giant planet. Nobody is squeezing it. The sun barely matters at that distance. From Pluto's surface, the sun looks like a very bright star, not the overwhelming nuclear furnace we experience on Earth. The only remaining explanation is internal heat, specifically the residual heat of radioactive decay in Pluto's rocky core. Radioactive elements like uranium and thorium decay slowly over geological time, releasing heat as they do. Every rocky world has some of this. The problem is that Pluto is so small that this heat should have dissipated into space billions of years ago. The math on heat retention for an object this size simply doesn't produce enough energy to drive convection in the present day. And yet there it is, convecting nitrogen ice, actively turning over, on a world where every equation says it shouldn't be possible. Nobody has fully explained this yet. That's not an exaggeration or a rhetorical flourish for dramatic effect. The current models of heat retention and radioactive decay in a body Pluto's size genuinely don't account for enough energy. Something else might be happening. We don't know what. The convecting ice plain was only one piece of an increasingly baffling picture. New Horizons found mountain ranges, real, dramatic, sharply defined mountain ranges made of water ice, some of them rising 3,500 meters above the surrounding terrain. That's comparable to significant mountain ranges on Earth. Water ice on Pluto isn't the soft, crushable stuff you find in your freezer. At minus 230 degrees Celsius, water ice is as hard as granite. It doesn't flow, it doesn't compress, it behaves like rock. And these mountains weren't eroded stumps worn down by billions of years of whatever passes for weather on Pluto. They had sharp edges and clean faces, features that suggest relatively recent formation, possibly within the last 100 million years in geological terms. Something pushed those mountains up, on a world that should have gone geologically quiet 4 billion years ago. Then there were the glaciers, and not water ice glaciers, nitrogen ice glaciers. Pluto has flowing rivers of frozen nitrogen that creep down from the highlands and pool into Sputnik Planitia, the same way glaciers on Earth flow into valleys. They move imperceptibly slowly, but the evidence is undeniable. Carved channels, flow marks etched into the surface, the characteristic signatures of material that has moved from one place to another over time. Active glacial systems, reshaping the landscape at temperatures where oxygen itself would freeze solid. Let that land for a moment. We struggle to keep asphalt roads intact through a single Midwestern winter. Pluto is running an active geological resurfacing program at temperatures that make our deepest winter look tropical. It is doing, right now, things that the largest rocky planets in our solar system stopped doing billions of years ago. Mars is bigger than Pluto, geologically dead. Mercury is bigger than Pluto, geologically dead. Earth's own moon is bigger than Pluto, geologically dead. Pluto, the tiny, demoted, forgotten dwarf, is the one still actively reshaping itself. If the convection and the mountains and the glaciers were extraordinary, what New Horizons found in Pluto's southern hemisphere was in a different category entirely. Right Mons is a feature roughly 150 kilometers across and about 4 kilometers tall, with a central depression at its summit that looks disturbingly, unmistakably like a volcanic caldera. When the New Horizons team first published the images, they were deliberately careful with their language. They called it a possible cryovolcano, a volcano that doesn't erupt molten rock, but instead ejects a slurry of water ice, nitrogen ice, ammonia, and methane from beneath the surface. The caution was scientifically appropriate. Claiming volcanic activity on a world this small and this cold is an extraordinary statement, and extraordinary statements require extraordinary evidence. The evidence kept arriving. The terrain surrounding Right Mons has almost no impact craters, indicating recent resurfacing. The texture of the surface around it is unlike anything else on Pluto, lumpy, hummocky, consistent with material that was pushed up from below and then froze in place before it could flow very far. Nearby, a second feature called Picard Mons shows similar characteristics but on an even larger scale. Together, they suggest that Pluto didn't just have geological activity in its ancient past. It may have had cryovolcanic eruptions within the last few 100 million years. Some researchers think significantly more recently than that. Think about what that means. A volcano, a real volcano, running on a fundamentally different mechanism but performing the same essential function. On a world receiving almost no energy from the sun, smaller than Earth's moon, at temperatures that defy the existence of any geological activity whatsoever. If you could somehow stand near Right Mons, you wouldn't see lava. You wouldn't feel heat. You'd be standing in near total darkness on terrain that crunches like packed snow, looking up at a mountain that once vomited ice into a sky so cold that the erupted material froze before it could flow very far. A volcano made of ice, on a world that shouldn't have the energy to run any geological process at all. It is one of the most genuinely alien landscapes ever documented in the history of planetary science, and we found it on the rock most people forgot about after a naming dispute. Here's something that surprises almost everyone. Pluto has an atmosphere. It shouldn't. Its gravity is too weak to hold onto gas for long. Its surface is too cold to produce much of it. And for a long time, scientists assumed that whatever thin envelope of gas Pluto might have had early in its history was long gone. But it's there. A thin but real layer of nitrogen, methane, and carbon monoxide extending up to 1,800 kilometers above the surface. Proportionally, relative to Pluto's size, it extends even further above the surface than our own atmosphere does above Earth. When New Horizons watched the sun set behind Pluto, an occultation that allowed scientists to analyze the atmosphere's structure, they saw it light up in layer after layer of blue haze. That blue is produced by tholins, complex organic molecules formed when ultraviolet light from the sun breaks apart methane and nitrogen in the upper atmosphere, and the fragments reassemble into larger, more complicated molecular chains. These tholins drift down and coat Pluto's surface in a reddish-brown stain. That distinctive ruddy color you see in every photograph of Pluto? That's not rock. That's organic chemistry, raining out of the sky. The surface is painted with the byproducts of atmospheric chemistry, continuously deposited, continuously renewed. But what makes Pluto's atmosphere truly remarkable is its behavior over time. Pluto's orbit around the Sun takes 248 years, and it's highly elliptical, meaning Pluto's distance from the Sun varies significantly over that orbital period. When Pluto is closer to the Sun, surface nitrogen ice sublimates, transitions directly from solid to gas, and the atmosphere thickens. When it moves farther away, the atmosphere begins to freeze back onto the surface and collapse. Pluto breathes. It inhales its atmosphere as it warms, then exhales it back onto the surface as it cools, on a cycle that takes nearly 2.5 centuries to complete. Scientists had predicted this general behavior. What they hadn't predicted was the complexity within that thin atmosphere. New Horizons detected temperature variations with altitude, distinct stacked haze layers, and evidence of actual wind patterns. An object with an atmosphere 100,000 times thinner than Earth's at sea level had identifiable weather systems. And that weather does things to the surface. Pluto has dark streaks on its terrain that align with prevailing wind directions, the same way sand dunes on Earth align with dominant winds. In 2018, a team of researchers published findings arguing that these features are wind-deposited ridges made of methane ice grains, dunes, on Pluto. The mechanism is unlike anything seen elsewhere in the solar system. Winds on Pluto are far too faint to loft particles by force. The atmosphere is simply too thin. Instead, as nitrogen ice sublimates on the sunlit side of surface features, the escaping gas kicks methane particles into the air, and the gentle winds carry them downwind until they settle into ridges. A completely novel dune formation mechanism, discovered on a world that was supposed to have nothing interesting happening on its surface at all. Every prediction was wrong, every single one. And now we get to the part that keeps planetary scientists up at night. Beneath Sputnik Planitia's nitrogen ice. Beneath the water ice bedrock. Possibly, and the evidence is genuinely compelling, beneath all of it, there may be liquid water, an ocean, on Pluto. The argument begins with a gravitational anomaly. Sputnik Planitia's position on Pluto's surface is not random. It sits almost perfectly aligned with the tidal axis between Pluto and its largest moon, Charon, the line connecting the two worlds' centers of mass. In orbital mechanics, that's exactly where you'd expect excess mass to accumulate, because the tidal forces between two tidally locked bodies pull heavy regions toward the axis over time. But Sputnik Planitia is an impact basin, a depression. It should be a region of lower mass, not higher. The only way to reconcile its position on the tidal axis with its status as a large basin is if there's something dense beneath it, adding mass that compensates. One compelling candidate, a layer of liquid water. Water is denser than ice, and liquid water mixed with dissolved ammonia, which acts as a natural antifreeze, lowering the freezing point significantly, fits the gravitational data. A study published in 2019 proposed an even more remarkable scenario, that this ocean might have persisted since Pluto's formation, protected from freezing not just by ammonia, but by a layer of gas hydrates. Gas hydrates are structures in which gas molecules become trapped inside a lattice of ice crystals, forming an insulating blanket. This layer, sitting between the ocean and the surface ice shell, would dramatically slow heat loss. potentially enough to keep liquid water stable for billions of years. If that model is correct, Pluto has maintained a hidden ocean for nearly the entire history of the solar system. Longer than complex life has existed on Earth, through ice ages and mass extinctions and the rise and fall of every civilization that has ever existed on this planet, there may have been liquid water sitting in the dark beneath Pluto's surface, undisturbed. Now comes the part that would have been career-ending to suggest a decade ago. Could anything live in that ocean? Let's be absolutely clear. Nobody is claiming there is life on Pluto. The evidence doesn't support that claim, and making it would be irresponsible. But the question of whether the conditions could theoretically be habitable is now, after the New Horizons data, a legitimate area of scientific inquiry. That shift in itself is extraordinary. Here's why it matters. For most of human history, and for most of the history of astrobiology as a field, the working assumption was that life requires certain fundamental conditions: sunlight, liquid water at the surface, a protective atmosphere, temperatures within a relatively narrow range, Earth-like conditions. The further something departed from those conditions, the less seriously it was taken as a potential host for life. But over the past few decades, biology has systematically destroyed that assumption. We've found microbes thriving in complete darkness at hydrothermal vents on the ocean floor, running entirely on chemical energy. We've found bacteria living inside Antarctic ice sheets. We've found entire ecosystems at the bottom of the ocean that have never seen sunlight, built on the chemical energy released by reactions between seawater and hot rock. Life, it turns out, is far less particular about its conditions than we assumed. If Pluto's putative ocean has a rocky floor, and models suggest it likely does, and if that rocky floor is even slightly warm from the core's residual radioactive heat, then you have the same basic combination that supports chemosynthetic life in Earth's deepest, darkest places: liquid water, mineral-rich rock, and an energy gradient. Not warmth, not sunlight, just chemistry, and water and rock. Nobody is saying there's life there, but a decade ago, nobody was saying it was worth thinking about either. The fact that we've crossed from obviously impossible to worth investigating is a testament to how thoroughly New Horizons overturned our understanding of this world. Pluto's story is complicated further by its relationship with its largest moon, or, more accurately, its binary partner, Charon. Charon is enormous relative to Pluto. At roughly 1,212 kilometers in diameter, it's more than half Pluto's size. This changes the fundamental orbital dynamic in a critical way. Pluto and Charon don't orbit each other the way Earth and the Moon do, with a small body circling a much larger one. Instead, both bodies orbit a common center of gravity, called the barycenter, that sits in the space between them, outside Pluto's surface. They're tidally locked to each other, meaning each one always shows the same face to the other. They spin together, facing each other permanently, orbiting their shared point like two dancers holding hands and spinning in place. Some scientists argue that calling Charon a moon is technically incorrect. They call it a binary partner. Together, Pluto and Charon form what may be the solar system's best example of a binary dwarf planet system. Charon's surface held its own surprises. New Horizons revealed a massive canyon system stretching across its equator, chasms running more than 5 times deeper than the Grand Canyon. Its northern pole is coated in a distinctive dark reddish cap that scientists have informally named Mordor Macula. The leading explanation for Mordor Macula is remarkable. Methane gas escaping from Pluto's atmosphere. Remember, Pluto breathes, periodically releasing its atmosphere into space, drifts across to Charon, gets trapped at its cold polar region, and is then processed by ultraviolet radiation into tholins. The same organic chemistry painting Pluto's surface in reddish-brown is being transferred across space and painting Charon too. Pluto is actively coloring its companion world with its own atmospheric chemistry. from hundreds of kilometers away. The system also includes 4 smaller moons, Nix, Hydra, Kerberos, and Styx, all of them small, irregularly shaped, and tumbling through space in chaotic, unpredictable rotations. Their spins aren't stable. They wobble and tumble because the gravitational field of the Pluto-Charon binary is itself complex and constantly shifting. If you were standing on any of these small moons and looking up, the sky would never look the same twice. Here's where we step back from the individual discoveries and look at what they mean collectively, because the implications go far beyond Pluto itself. Pluto lives in the Kuiper Belt, a vast ring of icy debris stretching from about 30 to 50 astronomical units from the Sun, beyond Neptune's orbit. It's estimated to contain hundreds of thousands of objects, ranging from small chunks of ice and rock to worlds potentially as large as Pluto itself. For most of the history of planetary science, everything in the Kuiper Belt was assumed to be essentially the same: inert, frozen, structurally simple, geologically dead, just rubble. Leftover material from the solar system's construction that never got incorporated into a proper planet. Pluto was the largest known object in this belt. The assumption was that if anything in the Kuiper Belt was going to be interesting, it would be Pluto. And since Pluto was obviously dead and boring, everything else could be written off. New Horizons demolished that logic from the foundation up. If Pluto, tiny, cold, distant Pluto, turned out to be this geologically active, this chemically complex, this full of unanswered questions, what does that say about the rest of the Kuiper Belt? What about Eris, which is roughly the same size as Pluto and orbits even farther out? What about Makemake, Haumea, or Sedna, sitting at the very fringes of the solar system in an 11,000-year orbit? We've been assuming they're boring because we've never looked properly. And we never looked properly because we assumed they'd be boring. That circular logic has now been exposed. The size determines complexity assumption. The idea that big worlds do interesting things and small worlds go quiet has been thoroughly disproven. Pluto is more geologically alive right now than Mars, more active than Mercury, more dynamic than the Moon. The correlation between size and geological activity that every planetary science textbook took for granted turns out to be, at minimum, far more complicated than we thought. And the implications keep expanding outward. If Pluto potentially harbors a subsurface ocean, other Kuiper Belt objects might too. Enceladus, one of Saturn's moons, has a confirmed subsurface ocean and actively vents water into space. Europa, orbiting Jupiter, is one of the solar system's top candidates for extraterrestrial life because of its liquid ocean beneath an icy shell. If ocean-harboring bodies extend all the way out to Pluto's distance, nearly 40 times further from the Sun, then the population of potentially ocean-bearing worlds in our solar system is dramatically larger than we ever imagined. Every icy world we haven't visited yet, and there are thousands of them in the outer solar system, could be hiding the same kind of complexity we found on Pluto. We've been dismissing entire categories of worlds based on assumptions that one spacecraft in one flyby proved were wrong. There is already serious discussion about returning. Not another flyby. That opportunity has passed, and New Horizons is now headed into interstellar space, an orbiter. Something that could stay in the Pluto system for months or years, watching the seasons change, mapping the surface in detail, and doing what New Horizons could only hint at, confirming or ruling out that subsurface ocean. One proposal, informally called the Pluto Orbiter and Flyby Mission, would carry instruments specifically designed to measure the thickness of Pluto's ice shell and detect the gravitational signature of liquid water beneath it, seismometers to listen for internal activity, cameras with resolutions far beyond what New Horizons could achieve in its brief pass, a suite of instruments designed not to photograph a world, but to understand one. The challenges are real and significant. The distance is staggering. A spacecraft launched today would take decades to arrive. The fuel requirements for orbital insertion at Pluto's distance are immense. Nuclear propulsion is likely necessary, which adds technical and political complexity. And the cost would be substantial in an era of constrained space science budgets. But consider what a single flyby accomplished. Consider that before July 14, 2015, scientists genuinely expected to photograph a featureless frozen ball. Instead, they got nitrogen glaciers, convecting ice plains, water ice mountains, cryovolcanoes, an organic chemistry factory in the sky, a possible ancient ocean, dunes built by winds too faint to feel. What would a dedicated orbiter find? The answer, based on everything we've learned, is almost certainly more. More complexity, more processes we can't explain, more questions that challenge the existing models, more evidence that the outer solar system is not a graveyard of dead, frozen debris, but a collection of active, dynamic, chemically rich worlds that we have barely begun to understand. Here's the real takeaway, and it's not really about Pluto at all. Every time in the history of space exploration that we've sent a spacecraft to something small, cold, and far away, something we assumed would be boring, it turned out to be extraordinary. Enceladus. We expected a dead snowball. We found active geysers venting water into space and a confirmed subsurface ocean. Titan. We expected a frozen rock with a thin atmosphere. We found a world with thick orange smog, lakes of liquid methane, and weather patterns eerily similar to Earth's water cycle, but running on a completely different chemistry. Triton, Neptune's large moon. We expected a cold, inactive surface. We found active geysers of nitrogen gas erupting from a world so cold it makes Pluto look warm. And Pluto, we expected the most boring object in the solar system. We found arguably the most surprising one. The pattern is consistent enough to be a principle. Our ability to predict what a world will be like before we actually go there is far more limited than we think. Our models are good, but they are not good enough. Our assumptions about what conditions are necessary for complexity, for activity, for chemistry, for geology, they are systematically underestimating what the universe is capable of producing. Which means there are thousands of objects in the outer solar system that we have mentally filed away as irrelevant, boring, or already understood. We haven't visited any of them up close. We don't actually know what's there. And based on the track record of every mission we've sent to something we thought we understood, the smart money is on being surprised again. Pluto is out there right now, 5.9 billion kilometers away. Its nitrogen glaciers are creeping. Its ice is convecting. Its atmosphere is cycling on its 248-year breath. Its possible ocean is sitting in the dark, undisturbed, waiting. We called it a planet for 76 years. Then we called it a dwarf planet and stopped paying attention. We spent 9.5 years flying a spacecraft to something we expected to be dead and found one of the most dynamic, complex, and baffling places in the solar system. The argument over its name was always the wrong conversation. Pluto doesn't care what we call it. It was never waiting for our classification, or our attention, or our understanding. It was out there doing extraordinary things regardless of whether we were watching. The question is, what else is out there, doing the same thing, in the cold and the dark beyond Neptune, waiting for us to finally show up and look properly? Because if Pluto taught us anything, it's this. The solar system's most spectacular secrets aren't hidden in places we think are interesting. They're hiding in plain sight, in the places we've already decided aren't worth looking.